Welcome to this coding walkthrough. In this session, we'll explore an interesting problem called delete nodes and return forest. We'll break it down step by step, analyze the approaches, and understand how to efficiently solve it. Let's dive in. In this problem, you are given the root of a binary tree where each node has a unique value. Along with the tree, you are provided a list of integers called to_delete, which specifies the values of nodes that need to be removed. When a node is deleted, the binary tree may split into multiple disconnected subtrees. Your task is to return the roots of all these resulting subtrees as a list, in any order. If a deleted node has children, those children become roots of new subtrees, provided they are not deleted themselves. Nodes that are not deleted will remain in their original positions in the tree. The input consists of the root node of the tree and the to_delete list, while the output is a list of tree nodes representing the roots of the resulting forest. Let's look at the first example. The input tree is represented as root equals 1, 2, 3, 4, 5, 6, 7, and the deletion list is to_delete equals 3, 5. The output we expect is 1, 2, null, 4, 6, 7. To understand this, we start with the initial binary tree, where node 1 is the root, with 2 and 3 as its left and right children. Node 2 has 4 and 5 as its children, while node 3 has 6 and 7 as its children. This structure forms the complete binary tree before any deletions are applied. Next, nodes 3 and 5 are deleted as specified in the to_delete list. When node 3 is deleted, its children 6 and 7 become new roots of separate subtrees. Similarly, node 5 is deleted, but since it has no children, it does not contribute to any new subtree. The result is a forest consisting of 3 subtrees. The first subtree is rooted at node 1, which now has 2 as its left child and 4 as the left child of 2. The second subtree is a single node, 6. The third subtree is also a single node, 7. These 3 subtrees collectively form our output forest. Now, let's consider a second example. Here, the input tree is given as root equals 1, 2, 3, null, null, 4, 5, and the to_delete list is 2, 4. The output we expect is 1, null, 3, null, 5. Initially, the binary tree has node 1 as the root, with 2 as its left child and 3 as its right child. Node 3 further has 4 and 5 as its left and right children, respectively. This forms the complete tree before any deletions are applied. In this example, nodes 2 and 4 are deleted. Node 2 is removed, and since it has no children, it does not contribute to any new subtree. Similarly, node 4 is deleted, and it too has no children, so no new subtree is formed from it. The resulting forest consists of a single subtree rooted at 1. In this subtree, 1 has no left child, and 3 remains its right child. Node 3 continues to have 5 as its right child. This subtree represents the entire output forest for this example. Finally, let's consider some edge cases that might arise in this problem. If the root is none, meaning the tree is empty, then the output should also be an empty list since there are no nodes to form subtrees. If the to_delete list is empty, meaning no deletions are required, the output should simply contain the entire tree as a single subtree. On the other hand, if all nodes in the tree are included in the to_delete list, the output will be an empty list because no nodes remain. Lastly, in the case of a single node tree, deleting that single node results in an empty forest, as there are no nodes left to form subtrees. To tackle this problem, let's first consider a brute force approach where we directly delete nodes from the tree. The intuition behind this method is straightforward. As we traverse the tree, whenever we encounter a node that needs to be deleted, we remove it and make its children the roots of new trees in the forest. This process involves checking each node to see if its value exists in the to_delete list. If it does, we remove the node, add its non-null children to the resulting forest, and then continue processing. While simple in concept, this approach has a major drawback. Searching for a node in the to_delete list takes m time, where m is the size of the list. When this is repeated for each node in the tree, the overall complexity can balloon to n² in the worst case. Additionally, handling the relationships between parent and child nodes manually adds to the complexity, making this approach less efficient and harder to implement effectively. A more efficient strategy involves using a recursive postorder traversal combined with a hash set. Here, the intuition is to process a node's children before deciding whether to delete the node itself. By converting the to_delete list into a hash set, we can perform quick O1 lookups to check if a node should be deleted. The process works as follows. First, we define a helper function that recursively traverses the tree in postorder. For each node, if its value is in the hash set, we add its non-null children to the forest and return none to indicate the node has been deleted. If the node is not in the to_delete set, we return the node as part of the modified tree. After the traversal is complete, we check if the root node itself is deleted. If not, it is added to the forest. This approach is highly efficient with an overall complexity of O(n), as each node is visited exactly once. Furthermore, the use of recursion naturally handles parent-child relationships, making the implementation cleaner and less error-prone. Another viable method is an iterative approach using level-order traversal with a queue. Here, we process nodes iteratively instead of recursively. Starting with the root node in the queue, we dequeue each node and check if it's in the to_delete set. If the node's value is found in the set, we add its non-null children to both the queue and the forest, and then remove the node. If the node is not in to_delete, it remains part of the current tree. This method achieves the same O(n) complexity as the recursive approach. However, it introduces additional complexity in terms of managing the traversal explicitly with a queue. While functional, this manual management can make the implementation harder to understand compared to recursion, which leverages the call stack for traversal. The optimized recursive postorder traversal was chosen as the final strategy due to several key advantages. First, it is efficient, with a time complexity of O(n) and a space complexity of O(h), where h is the height of the tree. Second, the recursive nature of postorder traversal naturally handles parent-child relationships, which simplifies the logic and avoids the need for additional bookkeeping. Third, by using a hash set for the to_delete set, we reduce deletion checks to constant time, further improving performance. Finally, this approach is highly scalable, as it processes large inputs efficiently without unnecessary overhead. Overall, it strikes the perfect balance between performance, simplicity, and maintainability while addressing the requirements of the problem. There are a few key observations and trade-offs to keep in mind with the chosen approach. First, converting the to_delete list into a hash set is a simple yet impactful optimization, reducing the search complexity from O(m) to O(1). Second, the use of postorder traversal ensures that a node's children are processed before their parent, which makes it easier to determine the structure of the resulting forest. While the iterative approach is an alternative, recursion is cleaner and avoids the need for explicit data structures like queues. The primary trade-off with recursion is its dependency on stack depth, which could lead to stack overflow in extremely unbalanced trees. However, this can be mitigated by using tail recursion optimization or switching to an iterative strategy if necessary. Ultimately, the recursive postorder traversal offers the best combination of efficiency, simplicity, and clarity for solving this problem. In this problem, we are working with a binary tree, where each node has a unique value, and we're tasked with deleting certain nodes specified in a list called to_delete. When a node is deleted, its children, if they exist, become roots of new trees. The input includes the root of the binary tree and the to_delete list, and the output is a list of all root nodes forming the remaining forest. To solve this efficiently, we first pre-process the to_delete list by converting it into a set. This allows us to check for deletion in constant time, making the algorithm more efficient. Using Python, this can be done with the simple line of code, to_delete_set equals set, to_delete. With this pre-processing step, we are set up for the next phase of the algorithm, which involves traversing and modifying the tree. The core of our solution relies on a recursive postorder traversal of the tree. Postorder traversal processes nodes in the order, left child, right child, and then the parent. This order is particularly important here because it ensures that we've already dealt with a node's children before deciding whether the node itself should be deleted. The recursive function accomplishes three key tasks. First, it handles the base case where the current node is none, which simply returns none. Second, it recursively processes the left and right children of the current node, updating their pointers as necessary. Finally, it checks if the current node's value is in the to_delete_ set. If it is, the node's non-null children are added to the result list as new roots, and the node is effectively deleted by returning none. If the node is not in the to_delete_ set, it remains part of the tree, and the function returns the node itself. Additionally, once the traversal is complete, we must also check if the root node itself has been deleted. If not, it is added to the result list. After completing the traversal, the result is a list of root nodes, each representing a tree in the remaining forest. Post-order traversal is key here because it allows us to manage subtree separations effectively when a node is deleted. The use of a set for the to_delete list ensures constant time membership checks, greatly improving efficiency. When a node is deleted, its non-null children are added as new roots, preserving the integrity of the forest. We also address edge cases such as when the to_delete list is empty, meaning no nodes are deleted and the entire tree remains intact. If the root node is part of the to_delete list, it's removed, and its children, if any, form the new forest. Lastly, if the tree itself is empty, we simply return an empty result. The data structures that enable this solution include the treenode class representing the nodes of the tree, a set for efficient deletion checks, and a list to store the roots of the resulting forest. Let's analyze the complexity of this algorithm. The time complexity is O(n), where n is the number of nodes in the tree. This is because each node is visited exactly once during the post-order traversal, and deletion checks are performed in O(1) time using the set. The space complexity is also O(n). The recursion stack can go as deep as the height of the tree, which is O(h), where h is the height. Additionally, the result list can contain up to n nodes in the worst case, such as when no nodes are deleted, and every node becomes a root. The code implementation begins with the pre-processing step where we convert the to_delete list into a set. Next, we define the recursive helper function. In this function, we process each node's left and right children first, then check if the current node itself needs to be deleted. If it does, we add its non-null children to the result list and return none. Otherwise, we return the node to preserve its place in the tree. If the recursive helper function does not delete the root node, we append the root to the result list at the end of the process. The function then returns the result list, which contains the roots of all trees in the resulting forest. For example, consider a tree with nodes 1, 2, 3, 4, 5, 6, 7, and a to_delete list containing 3, 5. When processing nodes, we find that node 5 is deleted, and since it has no children, no new roots are added. Similarly, node 3 is deleted, but its children, nodes 6 and 7, become new roots. Nodes 1, 2, and 4 remain intact, forming the primary tree in the forest. Finally, after processing all nodes, the resulting forest consists of trees with roots 1, 6, 7. Node 1 is the root of a tree with its left subtree intact, while nodes 6 and 7 become standalone trees as a result of node 3's deletion. Key optimizations in this approach include using post-order traversal to handle subtree separations effectively, leveraging a set for O(1) deletion checks, and minimizing space usage by modifying the tree in place. This ensures that the solution is both efficient and scalable, even for large trees. Here, we begin by defining the treenode class, which represents the structure of a binary tree node. Each node contains a value and pointers to its left and right children. Next, in the solution class, we define the delNodes method, which takes the root of the binary tree and a list of values to delete. We first convert the to_delete list into a set for faster lookups, as checking membership in a set is more efficient than in a list. We also initialize an empty list called result, which will store the roots of the resulting forest. Inside the delNodes method, we define a helper function that will perform a depth-first traversal of the tree. This function takes two arguments, the current node and a Boolean flag is _root, which indicates whether the current node is the root of a potential new tree. If the current node is null, we simply return none as there is nothing to process. Then, we check if the current node's value is in the to_delete_ set. If it is, this node will be deleted. Additionally, if the node is a root and is not marked for deletion, we append it to the result list as it represents the root of a new tree in the forest. The recursion continues as we call the helper function on the left and right children, passing the root underscore deleted flag to indicate if the current node is being removed. Finally, if the current node is deleted, we return none, otherwise, we return the node itself, allowing the tree to remain intact. After defining the helper function, we invoke it with the original root node and set the is underscore root flag to true, since the root of the input tree is initially the root of its own tree. The helper function processes the tree recursively, deleting the specified nodes and updating the result list with the roots of the new trees. Once the traversal is complete, we return the result list, which contains all the remaining trees in the forest. This approach ensures that we efficiently traverse the tree and construct the forest in a single pass, leveraging the recursive helper function to manage the node deletions and tree restructuring seamlessly. To solve the problem of deleting nodes and returning the forest, we begin by defining the tree node class, which represents a node in the binary tree. Each tree node has a value, a left child, and a right child. We then create the main solution class, where the delNodes method will handle the logic of the problem. Inside this method, we first convert the array of nodes to delete into a hash set. This allows us to achieve constant time lookup when checking if a node needs to be deleted. Next, we initialize an array list called result, which will store the roots of the remaining trees after the deletions are performed. Now, we proceed by calling a helper method that performs a depth-first search on the tree. This helper method takes the current node, the set of nodes to delete, the result list, and a Boolean flag indicating whether the current node is the root of a tree. If the current node is null, it simply returns null. Otherwise, we check if the current node's value is in the toDelete set, marking it for deletion. If the node is a root and is not deleted, we add it to the result list. We then recursively call the helper method for the left and right children, passing the root deleted flag to determine if the children become new roots. Finally, if the current node is marked for deletion, we return null to remove it, otherwise, we return the node itself, maintaining it in the forest. In this example, we are given a binary tree with the root node 1. The tree structure is shown, and we need to delete nodes 3 and 5. To begin, we initialize two key variables, to_delete_set, which contains the nodes to delete, and result, which will store the roots of the resulting forest. Starting with a recursive helper function on the root node, node 1, we check if it should be deleted. Since node 1 is not in the to_delete_set, it is not deleted, and because it is the root, we add it to the result list. Now, we proceed to handle its left child, node 2, while marking it as not a root. In the recursive call for node 2, we see that node 2 is not in the to_delete_set, so it is not deleted. We then explore its left child, node 4. At node 4, we again find that it is not in the to_delete_set, and since it has no children, we return it as is. Next, we move to the right child of node 2, which is node 5. Node 5 is in the to_delete_set, so it is marked for deletion. Since node 5 has no children, the return value for this call is none. After handling both children of node 2, we update node 2's left child to 4 and its right child to none, and then return node 2. Moving to the right child of node 1, we handle node 3. Node 3 is in the to_delete_set, so it is marked for deletion. As node 3 is deleted, we now explore its right child, node 6, treating it as a new root. At node 6, we determine it is not in the to_delete_set, so it is added to the result list. Since node 6 has no children, we return it as is. Returning to node 3, we find that, as it is deleted, the return value for this call is none. Finally, we return to node 1, the original root. After processing its children, we update its left child to node 2 and its right child to none. The recursive traversal is now complete, and our final forest consists of two trees, one rooted at node 1 with a subtree of nodes 2 and 4, and another is a standalone tree with root node 6. The output for this example is a list containing two trees, one with root node 1 and its subtree, and the other with root node 6. In the next example, we consider a simpler case where the root node itself is to be deleted. The tree structure is smaller, with only nodes 1, 2, and 3, and we are tasked with deleting node 1. We start by initializing the to_delete_set with the value 1 and an empty result list. The recursive function begins at the root node, node 1, which is also the target for deletion. At node 1, since it is in the to_delete_set, we mark it as deleted and transition to its left child, node 2, treating it as a new root. Node 2 is not in the to_delete_ set, so it is added to the result list. Since node 2 has no children, we return it as is. Next, we move to the right child of node 1, node 3, which is also treated as a new root. Node 3 is not in the to_delete_ set, so it is added to the result list. Similar to node 2, it has no children, so we return it as is. Returning to node 1, as it is deleted, the return value for this call is none. The final output for this case is a forest consisting of two separate trees with roots at nodes 2 and 3. The result for this example is a list containing two trees, one with root node 2 and the other with root node 3. Finally, let us consider a minimal example where the tree consists of only a single node, and that node is to be deleted. The tree has root node 1, and our to_delete_ set contains this node. The result list is initialized as empty, and we begin the recursive function at the root node, marking it as the root of the tree. At node 1, since it is in the to_delete_ set, we mark it for deletion. Node 1 has no children, so the return value for this call is none. With no nodes left in the tree, the final output is an empty forest, represented as an empty list. This concludes the walkthrough for the examples, providing a comprehensive understanding of how the algorithm processes trees and constructs the resulting forest after deletions. The time complexity of this solution is O(n), where n represents the number of nodes in the binary tree. Let's break this down step by step. First, we convert the to_delete list into a set. This step ensures constant time lookups for node deletions later, and its complexity is O(k), where k is the size of the to_delete list. Next, we perform a recursive traversal of the tree using a depth-first search. In this traversal, each node is visited exactly once, and its left and right children are processed recursively. This contributes a time complexity of O(n), since all nodes are visited only once. Additionally, for each node, we check if it exists in the to_delete_ set, which is an O(1) operation due to the efficiency of sets. If the node is the root of a new tree, it is added to the result list, which is also an O(1) operation. These operations are performed for every node, so they collectively contribute another O(n). When we combine these steps, we arrive at an overall time complexity of O(k) plus O(n), which simplifies to O(n), under the assumption that k is less than or equal to n, as is typically the case in this problem. The space complexity of this solution is also O(n). Let's consider the components contributing to this. First, the to_delete list is converted into a set, which requires O(k) space, where k is the size of the list. Since k is generally much smaller than n, this space usage is at most O(n) in the worst case. Next, we have the recursive call stack, which depends on the height of the binary tree. In the worst-case scenario, such as a completely skewed tree, the recursion depth equals the number of nodes, resulting in O(n) space. In the best case, with a perfectly balanced tree, the depth is O log n. Thus, the space complexity for recursion ranges from O log n to O(n). Lastly, we have the result list, which stores the roots of the resulting trees. In the worst case, where every node becomes a root due to deletion, the space required is O(n). When we sum these components, the total space complexity becomes O(n), as the other factors are either bounded by n or grow more slowly than n. Now let's compare this approach to a brute force or naive method. A naive solution might involve multiple traversals of the tree to identify and delete nodes, creating new tree structures along the way. This could result in a time complexity of O(n*k), where k represents the number of nodes to delete, since we may redundantly traverse parts of the tree for each deletion. The space complexity in such an approach would still be O(n) for storing the new tree structures, but the inefficiency of repeated operations makes it suboptimal. In contrast, the current approach optimally achieves the task in a single traversal, reducing the time complexity to O(n). It avoids redundant computations by processing each node only once and appending roots directly to the result list, which minimizes additional memory usage. When we analyze the best, average, and worst cases, the space used for recursion depends on the tree's height. A balanced tree results in O log n space for the call stack, while a skewed tree results in O(n). Regardless of the case, the time complexity remains O(n), as every node is processed exactly once. Finally, let's confirm the big O complexity of the solution. The DFS traversal guarantees that each node is visited once, solidifying the O(n) time complexity. The recursive calls stack up to the height of the tree, which contributes O(h) space, where h is the height. In the worst case, h equals n, making this component O(n), while in a balanced tree, it is O log n. Additionally, the auxiliary data structures, the to_delete_set and the result list, require O(n) space at most. This analysis demonstrates that the solution is asymptotically optimal in both time and space for this problem, with O(n) time complexity and O(n) space complexity as the final result. When solving this problem, there are several common mistakes to watch out for. First, failing to handle root deletion properly is a frequent issue. If the root node is in the to_delete list, you need to ensure that its children are added as new roots in the resulting forest. To fix this, explicitly check if the root is in to_delete before starting the recursive process. Next, it's crucial to update parent-child relationships post-deletion. When a node is deleted, its children must be detached correctly and added as new roots if they aren't also in to_delete. Forgetting this step can lead to dangling references. Another pitfall is incorrect handling of leaf nodes. If a leaf node is in to_delete, you might perform unnecessary operations or even encounter errors. A good fix is to specifically check for leaf nodes and treat them as a special case. Finally, modifying the to_delete list during traversal is problematic. This can introduce unexpected behavior or errors. Instead, convert the to_delete list into a set before starting, as this ensures constant time lookups without altering the original list. Another important consideration is efficient traversal. Using nested loops or redundant traversals can cause the solution to degrade to O(n²) time complexity, which is unsuitable for large trees. To address this, you should use a single traversal, such as DFS or BFS, to handle deletions and additions to the forest in one pass. Now, let's focus on some interview-specific insights. A key pattern here is to think of the problem as breaking the tree into disconnected components. When you delete a node, its subtrees become new roots if they themselves aren't deleted. This conceptual approach simplifies the logic. While recursive DFS feels intuitive for this type of problem, it's also worth being prepared for iterative BFS, as some interviewers prefer non-recursive solutions. Additionally, always test against edge cases, such as a single-node tree, a tree where all nodes are in to_delete, and one where no nodes are in the list. Lastly, for optimization, remember to use a set for the to_delete list to enable O(1) lookups and avoid repeatedly traversing the same parts of the tree. There are several related problems that build on similar concepts and can help solidify your understanding. For instance, LeetCode 236, lowest common ancestor of a binary tree, focuses on tree traversal and managing parent-child relationships, which is relevant here. Another example is LeetCode 450, delete node in a BST, which involves similar deletion logic but is specific to binary search trees. LeetCode 865, smallest subtree with all the deepest nodes, deals with subtree management and recursive traversal, echoing some of the strategies we use in this problem. Finally, LeetCode 652, find duplicate subtrees, also requires identifying and working with subtrees, making it another valuable problem to explore. In terms of alternative approaches, recursive DFS is often a go-to method. It's easy to implement and naturally aligns with the tree structure, but it does come with the risk of stack overflow for very deep trees. On the other hand, iterative BFS avoids recursion depth issues and processes nodes level by level, but it's slightly more complex to implement and requires additional data structures like a queue. Post-order traversal is another effective approach for this problem. One of its key advantages is that it ensures children are processed before their parent nodes, which simplifies the deletion logic significantly. However, this traversal order may be harder to conceptualize for some candidates compared to the more straightforward pre-order traversal. Another strategy to consider is the mark and sweep approach. With this technique, you first mark the nodes to delete in one traversal, then process the deletions in a second pass. While this method can be easier to reason about, it requires two traversals of the tree, which may be less efficient than handling everything in a single pass. Understanding these trade-offs and being able to choose the right approach for the problem at hand is essential for both solving this problem effectively and demonstrating your thought process in interviews. Great job! In summary, we tackled the delete nodes and return forest problem, focusing on tree traversal and node deletion techniques. Remember the importance of recursion and careful node handling. Thanks for watching, and don't forget to like, share, and subscribe for more engaging coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!